In today's lesson, we are going to be looking at angles in a circle. So this might be different from some of the concepts that we've looked at before, and this might be new to you as you may not have covered this in the previous grades. You should know, again, your kind of general angles. All triangles all angles in a triangle add up to 180. The different complementary and supplementary angles dealing with straight lines. We dealt a bit with that looking at the cast rule with trig. But these are going to be looking at specific cases with circles. So before we get into some of the actual theorems, we want to look at some definitions first, just so that we're kind of clear what we're talking about when we refer to some of these theorems. So the first one, we see a triangle, or we see a circle here. We're going to have our center. We have three different line segments. A line that goes through the center from one side of the circle to the other, from one edge to the other, that is called our diameter. If we have a line that only goes from the edge to the center, this is called our radius. And if we have a line that touches just one point on the edge of our circle, we call this line segment our tangent. So that's our tangent. A couple other things. We talked about having different lines that go through our circle. Our radius goes from the edge to the center. The diameter goes from one end to the other end through the center. If we have a line, like we see here, that goes from one edge to the other, but it doesn't necessarily go through the center, we would call this a chord. If we're talking about a portion of the circle that is cut off by a chord, we would call that a segment. In our circle, we might have two lines or two radiuses that form radii. I'm not sure what the plural is for that. They might form a portion of our circle, or the area or the line or the portion of the circle on the circumference that connects those 2 points. This is called an arc, or the arc length. And if we're referring to the portion of the circle occupied between those two radiuses or radii, and kind of joined by that arc length, that portion of a circle, this is called a sector area. So sector area and arc length we'll look at in the second half, or the second part of this lesson in a separate video, but we're going to be looking more at just the angles themselves in this portion. So we're going to be looking more at the terms tangent, diameter, radius, and so on when we talk about these different rules. So first, there are three inscribed angle theorems that we're going to be looking at. One is a right triangle theorem. Second one is called the bow tie. And the third one is called the Star Trek. And all of them are basically describing the shape that we're seeing in our circle. So if we have a triangle, I'm going to draw it here like such, we have a right angle. And the key thing here, one, the diameter is the base of the triangle. So we can see that our diameter is the base of our triangle here. So then that means that angle A, this angle, is always 90 degrees. So if we have a triangle, it formed in our circle where the diameter is the base or one of the sides, angle A is going to always be 90 degrees. Now our bow tie, you can imagine what a bow tie looks like. Looks something similar to this. So the way the bow tie works is that the corresponding angles use different symbols, and I'll go and highlight them as well. So these corresponding angles, right, are equal. So the corresponding angles are equal. So we have similar triangles. So these two share the same measurement. These two share the same measurement, as well as these two. So we have basically similar triangles or the same angles in the two different triangles. And finally, the Star Trek. So if you've ever seen Star Trek, you can probably see what this is going to look like. We have basically a Star Trek symbol. So in the Star Trek theorem, this is basically saying that the angle at the center, so the angle at the center, I'll draw in the center again just so we can see it. The angle at the center is always twice or 2 times larger the angle on the outside. So what that means is if this is considered x, and this angle here is considered 2x, or double our angle. And that is the Star Trek theorem. So these three are looking at kind of the angles inside of triangles, or inside of circles. And then the next two, we call them tangent theorems, right? There are no special rules for this. We just call it tangent A, tangent B. You don't really even need to call it that. There's not really special names. They're not really referring, or they don't have a unique shape similar to the last ones. These are going to be involving tangents in our circle. So the first one is talking about tangents in general. So if I were to draw a tangent, best if I can, so this line would technically, let me draw it a little bit different. This line would technically be touching our circle at one point only. And if we were to draw a radius out to that point, it is going to form a 90-degree angle. Same if I draw a tangent here, it's touching the circle at one point. Oops, that's not even close. If I draw a radius out, it will meet that tangent at 90 degrees. So the radius or tangents are always 90 degrees to the radius. Tangents are always 90 degrees or perpendicular to the radius. Tangent B is saying if I have two tangents, let's say I draw one tangent here, I draw another tangent here. Oops, if I draw two tangents, right? Again, we know that they are going to be 90 degrees to the radius, but they share a common point. They meet at a common point. We'll call it A. And what this second theorem is looking at is if these two tangents going to the points where they touch the circle, call it B and C, so where they touch the circle, those two line segments, or the distance from each tangent to A, is equal. So these two angles are equal, or sorry, two sides are equal, which makes sense because we have two angles that are equal here. So it does make sense that they would be kind of identical in length as well. So in this rule, AB equals AC, so the two line segments equal, and this is when two tangents are drawn through a common point. And essentially the two tangents could, well, unless they're directly across from each other, making them parallel, chances are that they might eventually meet at some point. So those are the different theorems that we're going to be looking at. So now what we're going to do is just kind of work through a couple problems to find missing angles using what we know. So we're just going to go through one by one. if I look at the first one, I want to find the measure of angle CAB. And when I talk about this to help us find angles, the middle value is the point or the vertex for the angle we're looking for. So I would read this as CAB. I'm looking for this angle here. Right, so that middle value or that middle variable, that is telling us what angle we're looking for. So I'm looking for this unknown angle. I do see that we have a triangle. The base of the triangle is a diameter, so that means that this angle is 90 degrees. So then this angle here has to be 180 minus 90, which is equal to 32 degrees. So I'll switch up the size of the pen. So this angle here has to be 180 minus 90, so 32 degrees is this angle. Here, I want to find the measure of XZY. So I want to find this angle right here, XZY. This is the bow tie theorem, so hopefully we recognize that it's shaped like a bow tie. So that means the corresponding angles are equal, so that's 52 degrees. This would be 41 degrees. And depending on which one we want to do, if we want to find this angle here or the other side, it will work out to the same. Regardless of which one we look at, we have to do 180 minus 41 minus 52 equals 87. That reminds me, I have to go back to this one. It's not 32. Did the math wrong. It's 180 minus 90 minus 32 equals this angle, which is 58 degrees. So that's a little mistake on my end. Oops. So 58 degrees is angle A, going back. And angle Z or XZY is 87 degrees. This one, angle SUT. So SUT, I'm looking for this angle up here. So that means I need to figure out, we see two kind of rules here. We see our tangent theorem because we see two tangents that meet at a common point. So that means, it doesn't really mean too much. We don't care too much about these side lengths, but we are concerned, or it is helpful to know that this angle here, we see here, this angle is 90 degrees. Same with this angle here. Because if I know these three angles, I can figure out this third one, because all angles in a triangle have to add up, or not all angles in a triangle, sorry. This is a four-sided figure. 1, 2, 3, 4. So 4 sides. So that means all the angles have to add up to 360 degrees. So 360 minus 90 minus 90 minus 50 equals 130. And we know that this angle here is half the size, because this is the Star Trek theorem, right? This based off of these lines here. It's our Star Trek theorem. So this angle is 130 divided by 2, or 65 degrees. So here is 65 degrees. So combining two of the theorems that we've looked at. MON, so again, we're looking for this angle here. This one is relatively straightforward. Again, it is the Star Trek sign or Star Trek theorem. So it is going to be double our measurement or on the outside. So 54 times 2, we get 108 degrees. The next one, QPR. So we're now looking for this angle out here. So kind of the opposite of one of the ones we just did. I know this angle S is 61, so that means the angle around the center, QOR, is going to be 61 times 2, which is 122. 61 times 2 equals 122. And because we have two tangents that meet at 90 degrees, this third angle here is going to be 360 minus 180, or minus 90 minus 90 minus 122, and we get 58 degrees as well. And again, the reason we're subtracting it from 360 is because we have a 1, 2, 3, 4-sided figure. So the angles in a 4-sided figure add up to 360 degrees. JLK, again, Star Trek theorem, it is half of my inside angle. So 102 divided by 2, we get 51 degrees. BCX, so BCX, we have our bow tie rule or bow tie theorem. So we have 94 over here. So that means that this angle here is going to be 180 minus 94 minus 58, which gives us an angle of 28 degrees. Angle Y, so again, we have a tangent here. So it meets at 90 degrees. So this angle here is going to be 180 minus 36 minus 90, which equals 54 degrees. Similar to this one, so this one is combining a bit of our tangent kind of rule. It's also looking at the inside angles, or some of the other the Star Trek rule and some of our complementary and supplementary angles. So this is, if this is 45 here, then we know that X has to be double that, or 90 degrees. So this is actually a right angle. Because it's at the center and the two sides are going out to the edge of the circle, these two sides are the same. They're considered, they're each a radius, so they're the same measurement. So this is an isosceles triangle. An isosceles triangle tells us that these two angles are also the same. So if this is 90, then these two angles here have to be the same. So together, if we say X, X, and 90 have to be 180, and these two angles have to be 90 divided by 2, because that's how much has to be split up evenly between both of them, or 45 degrees. So these two angles inside are 45 degrees. So we're finding a bunch of extra information first to help us find y. Now, if we look at this, we don't really know if we have any parallel angles or parallel lines, but we should be able to determine that if we have 45, we found X is 90. We can argue, or let's take a look at this and see what else can we find. So with this one, there is some kind of additional information. Oops. There's some additional information. Sorry, I had to actually look that one up, I'll be honest. There is some addition. There's one extra theorem. It's basically stating if we have a tangent, we see a tangent here, and a chord. The angle between a tangent and a chord, so for example, if I'm looking at, say, this 70 degrees here, right, this is between the tangent and the chord, right, if the chord were to continue. This angle here is equal to the angle of another additional segment, or the same chord in an alternate segment. So basically it's saying this angle is equal to all of this over here because of the fact that we have it's another angle and joining with our tangent. So it's a different theorem. We didn't talk about that one because it's a very specific case, but essentially it's saying that this angle here has to equal 70. So now we can figure out y. So y would be 70 minus 45 degrees, which is going to be 25 degrees. So that angle y is 25 degrees. So a small little, it's a unique situation, but you have seen it now. So you can use that if you come across the same types of questions. Here, again, this one is straightforward. This inside angle is double the outside, so this is going to be 120 degrees. MLN, again, the same idea. So this inside is going to be double our outside one, or 96 divided by 2, which is 48 degrees. And then finally, C is a point in the circumference of the circle such that CAB, so this angle here, is equal to twice the size of this angle. So this would be 2x, you could say, and this would be x. And I want to know what is the size of this smaller angle. Well, because the base or one of the sides is the diameter, that means this angle has to be 90. So these two have to add up to 90 as well. So 2x plus x equals 90, or 3x equals 90, x equals 30. So that means the angle B here is 30 degrees, and over here it is 60 degrees. So those are the two kind of, these are some examples of the laws, or theorems that we're looking at. I'll scroll back up to those because those are the most important part. So we have our 5 different theorems here. Again, make sure you're practicing and working through some of these problems because there's not really, again, a cookie cutter way to do this. You're gonna have to kind of look to see what theorems we can see, maybe play around with some of the ideas of, again, that we've looked at previously in terms of circles, where we have, or angles in general, right? Angles in a triangle add up to 180, a 4-sided figure is 360, and so on, things like that. But these are the 5 that you're more than likely going to be seeing when dealing with circles.